Hello, everybody. Good afternoon and good morning, good evening. We now start the last section of this meeting. The first speaker will be Kuantay Boshkaev. Please, Kuantay.
Okay. Hello, everyone. So, before starting, I would like just to thank all the organizers of the conference, including Professor Fini, Professor Rahimuradi, and Professor Soroush Shakeri. So thank you very much for giving me this opportunity to present our recent paper. So it was recently accepted by PRD, and you can also find on arXiv. And this work is done in collaboration with PhD students and also with professors from Italy and Mexico. Quevedo is from Mexico. So this is the outline of my talk. And as you can see, I will speak about Q metric, Ker metric, and then in the end, I will speak about radiative flux, spectral luminosity of accretion disks around these compact objects described by the Q metric and Ker metric. And of course, in the end, I will just summarize and conclude. So my motivation comes from the fact that the theory of black hole accretion was developed in early 70s by Novikov Thorne, Page Thorne, and also by some prominent scientists from post-Soviet Union countries like Univ and his colleagues. And this theory was successfully applied to astrophysical black hole candidates in order to explain their observed spectrum for many years. Only relatively recently, there were some attempts to consider space-time around astrophysical compact objects that depart from the Kerr line element. So you can see here some references, and you can find also some details from the references indicated in these papers. So here we consider the so-called Q metric. I will give you later the details. We investigate circular motion of test particles, calculate the orbital parameters, such as angular velocity, energy, and angular momentum. And of course, we need them in order to calculate also the radius of innermost stable circular orbits, plus all the quantities that can be observed from the accretion disk surrounding compact objects. So radiative flux, differential and spectral luminosity. And in addition, we also calculated the efficiency of the emission. And in order to compare our results with the well-known results for the Schwarzschild and Kerr metric, we also consider these cases with the Schwarzschild and Kerr metrics. So here I just review of Q metric, and this solution is the vacuum solution of Einstein equations. It describes static axially symmetric deformed objects. And as you can see, it contains only two parameters. M is the mass parameter, Q is the quadrupole parameter. And in the limiting case, when Q is equal to 0, one can recover the Schwarzschild solution. And usually this Q metric is known in the literature as gamma metric, as delta metric, and also known as Zipoy-Voorhees metric. Nevertheless, we just call it Q metric in order to stress the importance of the parameter Q that is related to the mass quadrupole moment of the source. So it describes the gravitational field around the deformed compact objects. So for this metric, we calculated orbital parameters using standard procedure in the literature, especially in general relativity. So these are the angular velocity of test particles, this is the energy, and this angular momentum. And these quantities we need in order to calculate further the spectrum of the accretion disk. So one of the important physical quantities is the radius of innermost stable circular orbits. So for the Q metric, we have it in this form. And here we have two roots with plus and minus sign. And in our computations, we used only plus sign because it is the physical solution, and minus sign is not physical, as it can go below photospheric radius, and even it can go below the event horizon in the Schwarzschild case. So we took only plus sign, and also we calculated the total mass using the well-known procedure of definition of multiple moments given by Geroch and Hansen. So the total mass of the source in the presence of quadrupole parameter will be given by this formula. And then we just made normalization with respect to the total mass and obtain this formula. So it will be used for our further computations. So in addition, in order to compare our results with the well-known Kerr metric, we considered Kerr metric. It is also two-parametric solution of Einstein equations. M is the total mass, and A is the Kerr parameter. So I guess everybody knows about this metric. And we introduced also additional parameter, A over M, and denoted as J. And this parameter is called spin parameter, or simply dimensionless angular momentum. In some computations, it's really convenient to use dimensionless quantities as J. So for the Kerr metric, we just reproduced all the known results in the literature, especially from the paper by Bardeen et al., I think late 60s. So just to make sure everything is correct. And then we also calculated the radius of ISCO. And as you can see, for the Kerr metric, the ISCO radius is complicated with respect to the Schwarzschild, because in the Schwarzschild we get only 6. This already a normalized quantity, but in the case of Kerr metric, we can have different values. So here we took positive sign, and it means that we just focused on the co-rotating orbits around the black hole in this case. The minus sign is just we neglect because it describes counter-rotating orbits, and for counter-rotating orbits, the value of ISCO usually is larger than the Schwarzschild case. But for co-rotating case, when we take plus sign, the ISCO is smaller with respect to the Schwarzschild case. And we exactly need the value of ISCO, which is smaller than Schwarzschild case. Only in that case, the luminosity and the flux of the accretion disk will be larger, again, with respect to the Schwarzschild black hole. So, and here we also use a very well established formalism by Novikov Thorne and Page Thorne. So we use their definition of the flux, and here all these quantities are known, and m dot is the accretion rate, and we just adopted it to be constant. And we can, for example, in our computations, we just put 1. But of course, one can use different values and to get different flux. And this quantity is the simply determinant of the metric. But here is for three-dimensional space, subspace. So this is also a crucial quantity. It is called differential luminosity. And once we know the flux, we can also calculate differential luminosity. And then by integrating this equation, we can get the net luminosity. So the net luminosity usually is measured. So it is the luminosity that reaches observers at infinity. And this quantity represents the amount of rest mass energy of the accreting matter that is converted into radiation. So in other words, the efficiency of the source in converting infalling mass into emitted radiation. So just to remind you, this quantity for Schwarzschild black hole is around 5.72%, so around 6%. But for the Kerr metric, depending on the value of the angular momentum, and for the Q metric, depending on the value of the quadrupole parameter, this quantity can be different, can be large or can be smaller. So I will show you later also. So in this slide, I just show you the definition of the spectral luminosity. And we introduced here also dimensionless quantities. So just we wanted to make sure that our results will not depend on the mass. So everything is normalized with respect to the total mass of the source. And for the Q metric, total mass is defined by this expression, and for the Kerr metric is simply the mass of the source. So here all the quantities are known, so we take from the orbital parameters, and this UT is the time component of four-dimensional velocity. And of course, for the Q metric, since there is no rotation, this term should be neglected. But for the Kerr metric, it is still not, it is valid. So one should take into account. So we just denoted Y, the frequency of the accretion disk. So this is the notation that is also used in the literature. So flux is normalized with respect to the total mass with this expression. So here we present the ISCO, normalized ISCO, as a function of the quadrupole parameter for the Q metric. So this black solid curve indicates the dependence of ISCO on the quadrupole parameter. And red dashed curve indicates the ISCO of the Kerr metric. So as you can see, they cross each other exactly when Q vanishes, when J vanishes, and it is exactly for the Schwarzschild black hole. So the crossing point gives us exactly ISCO for the Schwarzschild black hole. And in this plot, we show dependence of J on Q. So it is the degeneracy for the ISCO. So we just took definition of ISCO for the Q metric and definition of the ISCO for the Kerr metric, equated them, and from that expression we just found the dependence of J on Q. So here we just show that for each given value of the quadrupole parameter, there exist the values of the spin parameter, and for these values everywhere the ISCO will be the same. So here we show the angular velocity of test particles in the Q metric. So we choose different values of the parameter Q, and this black solid curve shows the angular velocity of a test particle in the Schwarzschild case. So we focused mainly on positive values of the Q, simply because positive values of Q correspond to the oblate astrophysical objects. But if we take, for example, negative values, then it will be prolate astrophysical object, which is highly unlikely. So we mainly observe rotating so astrophysical objects, and their shape is oblate, not prolate. So of course for the Q metric there is no rotation. So, and we just compared angular velocity obtained through the Kerr metric, and we see that for co-rotating orbits, when J is positive, the angular velocity of test particles will be less than Schwarzschild case. And for negative values of J, which correspond to the contra-rotating orbits, the angular velocity of test particles will be larger than Schwarzschild. And as you can see, in the case of angular velocity, we can see the similarity between positive values of J and positive values of Q can give us similar results. Then we also constructed angular momentum, and in this case, angular momentum in the Q metric will be larger than the Schwarzschild case. And here we also observe a different picture. So angular momentum, when angular momentum is negative, the angular momentum of test particles will be larger with respect to the Schwarzschild, and vice versa. When J is positive, will be smaller than Schwarzschild case. So in this plot, we constructed energy. So as we can see, again, for oblate objects, energy of test particles will be larger with respect to the Schwarzschild case. But for the Kerr metric, we see for the negative values of J, only in this case, the energy of test particles will be larger with respect to the Schwarzschild black hole. So knowing all the parameters in the previous plot, we can construct now the flux of the accretion disk. And as you can see, for distances closer to the central object, we see that flux in the case of Q metric will be larger than Schwarzschild case. But as soon as we go far from the source, we see that the flux of the accretion disk, flux of the emission coming from the accretion disk is smaller with respect to the Schwarzschild black hole. And here we will do the same, taking into account the Kerr metric. And as I told you earlier, for co-rotating orbits, the ISCO will be smaller, and that's why the flux will be larger with respect to the Schwarzschild case. And for contra-rotating orbits, the ISCO will be larger than Schwarzschild case, and correspondingly the flux will be less. And in this plot, we see that we see the differential luminosity with respect to the normalized radial coordinate, and the effects that we observe in the flux automatically translate into the differential luminosity. So the same behavior for co-rotating orbits, the differential luminosity will be larger. So, and here we plot the spectral luminosity, which is observed. And as we can see, we should consider low frequency region and high frequency region. For the Q metric, when we consider low frequency region, then the luminosity will be larger with respect to the Schwarzschild case. So here we see this is the Schwarzschild, and these are the for the Q metric. And for higher frequency region, we see the opposite picture. So it means that for higher frequencies, the Q metric will give us a smaller value with respect to the Schwarzschild black hole. But in the case of Kerr metric we see that spectral luminosity for co-rotating orbits in all frequency range is always larger with respect to the Schwarzschild black hole. But for counter-rotating case, the spectral luminosity is always less than the Schwarzschild black hole case. So when we submitted this paper to the journal, the referee asked us to overlap these pictures, and just to make sure that for some values of Q and for some values of J, we can get the overlapping. So by overlapping, we mean that the astrophysical compact object described by the Q metric can mimic the Kerr black hole. So in the next slide here, we did what the referee asked us. So here we have some values of J, here we have some values of Q, and we overlapped all these plots. And as we can see, for small values of J, at smaller frequencies, this curve overlap. For example, here we see overlapping value, and here we see overlapping value. But at higher frequencies, we don't see this overlapping. So one can observe, for example, astrophysical compact object and measure the spectral luminosity in different frequency range. And of course, we can say at low frequency range, this object can mimic the Kerr black hole, but at larger frequency range, they can be distinguished from each other.
3 minutes left. 3 minutes left.
Yeah, okay, I have only 2 slides left. So here we have similar plots, and here we just wanted to show that for specific values of J, of spin parameter, here we took negative values. We observe different pictures. So here at high frequencies, the Q metric can mimic the Kerr black hole. So here we just show the differences between the spectral luminosities obtained by the Q metric and obtained by the Kerr metric. And as you can see, these differences cross this 0. It means that for these crossing points, the spectrum cannot be distinguished. So we can say that the Kerr black hole, for this, having these values of the spin parameter, cannot be distinguished from the Q metric possessing these values. And here we did the same, but for counter-rotating orbits, and we see also the same, similar picture, let's say. For specific values of Q, there is always specific value of J, and in that case, we cannot distinguish these objects. So we also here calculated the efficiency for the Q metric, and as you can see, the efficiency of the Q metric for oblate objects always smaller with respect to the Schwarzschild black hole, because when it's 0, we'll get exactly Schwarzschild black hole efficiency. But as I told you, negative values of Q correspond to the prolate objects, and that is not the case. And of course, in that case, we see that the efficiency could be larger. So here we just equated efficiency for the Q metric and Kerr metric, and found from that equation the dependence of J on Q. And as you can see, for these values of Q, there is always values of J. And in that case, we get the same efficiency. So in the conclusion, I would like just to stress that here we use the toy model and try to see how can we distinguish Kerr black hole from the deformed astrophysical compact object. So, and of course, this toy model is simplified, but in real cases, of course, the spectra emitted by accretion disk are much more complicated. So one should take into account the plasma in the thick disk. Also, one should take into account magnetic field and other parameters. So anyway, we believe that the general consideration obtained here do indicate a road towards the possibility in the future of experimentally constraining geometric quantities such as mass quadrupole moment of compact source, and thus answer the question whether astrophysical black holes are indeed described by the Kerr metric. So thank you for your attention.
Thank you, Kuantay. We have a couple minutes for questions, please.
Okay. So
could I ask a question? Could I ask?
Yes, yes, please.
It's Alexander Zakharov is speaking. So you propose some metric. I know this activity, but I do not understand completely sense. Because it's, do you know gravity theory? There is real solution.
Yes.
Or do you use general relativity? Because in principle, you could substitute your metric in the left-hand side of Einstein equation, and after that you could calculate stress energy tensor. Of course, you could do this procedure. In this case, I don't know shape and also property of stress energy tensor in this case. Or in other words, where is this theory, gravity theory solution? Because beauty of Schwarzschild, Reisner, Nordström, and Kerr, they are exact solution of Einstein equations. Thank you.
Okay. So this solution that we use is also the exact solution of Einstein equations in vacuum. So we don't take into account the energy momentum tensor. And this solution was obtained by Zipo Voorhis long time ago, and it's widely used. So it describes the deformed object, axially symmetric. So we can describe any astrophysical object that is not rotating, but deformed with this metric. But we don't know exactly what is the source of this object. So we believe that it can describe the naked singularity. So.
If it's vacuum solution, it's violate Birkhoff theorem. Because it's not Schwarzschild metric, it's different. Because Birkhoff theorem is stating that you have to have Schwarzschild solution in the, I mean, outside of body. But it's clearly, it's not Schwarzschild solution. What about Birkhoff theorem in this case?
Yeah, I know, but I'm not saying that this is Schwarzschild solution. I'm saying that when Q vanishes, we will get Schwarzschild solution as a limiting case.
No, I understood it. I understood, but you consider non-vanishing Q value.
Yes,
so in this case, but in this case, it's not Schwarzschild solution. It's violation of Birkhoff theorem. If you are in general relativity, you have to have Birkhoff theorem.
Yes, I know, but that is only for Schwarzschild. But here we consider not the black hole solution. We consider other solution that departs from the black hole. And it is still the solution of Einstein equation.
Okay, I'm sorry, I have to close the discussion. You can discuss it privately. We have to move to next speaker, who is Professor Carenza. Please share your screen and go ahead.
Okay, let me stop sharing.
Hello? Yeah, you stop your sharing.
I think you already stopped.
Okay.
Sharing.
I hope that you see my screen.
Yeah, I see your presentation.
Right?
Oh, yeah, also picture too. Good. You are ready. Please.
Okay, perfect. Okay, so hello to everyone, and thanks for this kind invitation. I hope that the next time we can do it in person. So now we are approaching the end of this workshop. So I will try to give you this presentation on a very frontier of the astrophysics, which is axions. Axions are exotic particles, hypothetical particles, introduced to solve the strong CP problem, which is this problem of the QCD, for which we have an extra term in the QCD Lagrangian, which should break the CP invariance of the theory. And so it should induce a neutron electric dipole moment, which is very big. But experimentally, we measure this quantity, and it's small. So it means that this parameter entering in the QCD Lagrangian should be very, very small, which is quite natural. So this is a naturalness problem. Why theta QCD is so small? This is the strong CP problem. To solve this problem, the axion is introduced by the so-called Peccei-Quinn mechanism. In this mechanism, we have an extra U1 Peccei-Quinn chiral global symmetry. And this symmetry is not observed in our experiment, so it's broken at a very high energy scale, which is called Peccei-Quinn scale, FA. After the breaking of this symmetry, the Goldstone boson of the theory is the axion, which couples in this way to the CP-odd part of the QCD Lagrangian. So, thanks to the QCD dynamics, this term goes to 0, and naturally we solve this problem, driving dynamically the CP-odd term to 0. So axions are particles that in general are introduced to solve this problem, and they are coupled with fermions in this way and with photons too. But let's see something more in details. So these are the two main coupling of axions. So axions can decay, for example, into photons, and can be produced by fermion in fermionic processes. These processes are very important for axions and their role in astrophysics because these are the main production and detection axion mechanism from axion produced in supernovae or other kind of stars, as we will see. Just a small comment before starting. Axions, QCD axions, the one introduced to solve the strong CP problem, have a very low mass and a small coupling with photons, which are suppressed by the inverse scale of this Peccei-Quinn energy, which is typically very, very high, and so these two quantities are very, very small. But this is only for an axion in QCD. In general, other UV completion of the standard model introduce also a more generical structure, more generical particles, which are called axion-like particles. Axion-like particles have a lot of different properties, and they don't need to satisfy this relation. So we can also have very heavy HALP, important for searches at colliders, or on the opposite side, super light HALPs that work as fuzzy dark matter in the range 10 to the minus 20 electron volts, something like that. In other model, ALPS can also be coupled with Young-Mills sectors to dark Young-Mills sectors to be the inflaton, or something else also. They can also induce Flavier-violating processes. So we have a plethora of different situations and properties for axion-like particles, which are a very general prediction of UV completion of the standard model. So these are the main motivation to study axions and axion-like particles, because they are predicted required by the standard model and by completion of the standard models, and they can act also as dark matter, and there is a strong experimental effort to search axions in these years now. So it's a very interdisciplinary research, and it's extremely important for the future of astrophysics and cosmology. So let's start with the discussion of axions and ALPS in low mass stars. Axions can be produced in various kinds of stars. In this example, I'll show you the impact of axions on the evolution of low mass stars. As you see, this is the Hertzsprung-Russell diagram, color magnitude diagram for a star. For stars, every point is a star which belongs to a different phase of its evolution. Now we will focus in this part of the diagram in which the star now has burnt hydrogen in the core to contrast the gravitational collapse, and the core now is composed in the red giant phase by helium, which cannot be burned because the temperature is not high enough to burn helium. But there is still a shell of hydrogen that is burned to contrast the collapse. And so this is the so-called red giant phase that you see here in this part of the diagram. After this phase, when the temperature reaches a value enough to ignite the helium burning, so we enter into the horizontal branch, the name given to this part of the Hertzsprung-Russell diagram. In the horizontal branch phase, so the coal is also in the core is burning helium, and so we will focus mainly on this phase because the star is very hot and dense, so it could produce axions and axion-like particles. The main production mechanism for axion-like particles in this environment are the Primakov conversion, which is given by the two-photon coupling. So one photon converts into an axion into an external field, electric field of ions in the star, or there is also the other process in which the second photon line is another real photon, so two photons scatters to produce an axion. This is typically important at higher axion masses. With these two processes, axions are produced in the star and they escape, subtracting energy to the core of the star. So the evolution becomes faster and faster. But observationally, we know we can measure this ratio R, which is the ratio of HB to red giant stars. This number is calculated by counting the points in the Hertzsprung-Russell diagram. So if we see a lot of HB stars, it means that the HB phase is very long compared to the red giant. So in this ratio, I mean. And this value is given by 1.39. So this number is important because it's measured, and we know that given the measurement, the errors, the uncertainties, this ratio cannot be reduced more than 15%. So we have, in this case, a measure of the duration of the HB phase compared to the red giant phase. Axions are active only in the HB phase because the star is hotter, and so it's interesting to see what is their impact on this parameter. And so we run different simulations with different parameters of the axion, mass and coupling with photons, to determine when this parameter, this ratio, is reduced by more than 15%, so putting a constraint on the parameter space of axions. Here you see the parameter space of axion, G gamma, the coupling with photons, against the axion mass. And the region excluded by this bound is this red region here. So every point inside this region would produce a too fast cooling of the HB. And so it's excluded for this reason. Here you see that there are also other constraints coming, for example, from the supernova that we will discuss in a moment, and also from other laboratory experiments, which are the beam dump experiments, which are very useful to study axion in this mass range, in this high mass range. So you see a nice complementarity between astrophysics on this side and laboratory experiments here. And this is a peculiar characteristic of axion searches. Now let's consider supernovae, which are the final phase of a massive star. Massive star burns lighter element, and then in the end, its core is composed by iron, which cannot be burnt. So the gravitational collapse cannot be stopped, and the envelope crashes on the core, shrinking it to very high density, and the outer envelope bounces back in the so-called supernova explosion. In this situation, the core becomes a proto-Newton star, which is a very extreme environment because the density is the same of nuclear matter, is very, very high, 10 to the 14 grams per centimeter cube. The temperature of a supernova core is the hottest place in the universe, not compared to this one that you find Googling. And the temperature is about 30 MeV. And some kind of supernovae could also host very strong magnetic fields around 10 to the 15 Gauss. So it's an extreme environment, and it's useful to probe very light and weakly interacting particles. This is what we know from supernova. The only galactic supernova observed with our modern instrument was supernova 1987A, and we collected these few neutrino events given by the neutrino produced in the supernova explosion, then interacts in the detector by producing positron by this process. And this is the energy of the produced positron against the time of the burst. These points are, despite their sparseness, they are important to constrain what we know about supernovae. And it seems that a standard supernova model without exotic particles agrees very well with these observations. So any exotic particles cannot disturb too much this picture. And this is the origin of the so-called energy loss argument. So if there are axions inside the star, which are produced and they escape subtracting energy to the core, they cannot subtract more energy than neutrinos, which is the standard energy loss channel. So we can put this bound to constrain axion properties for axions produced in supernovae. Axions typically are produced in supernova by their coupling with nucleons by this process, which is the nucleon-nucleon bremsstrahlung. Two nucleons scatter each other by exchanging a strong mediator as a pion, and one of them emits an axion. Axions produced in this way are, this is not the only mechanism to produce axion in supernova core, because the other mechanism, which is also important, is this one, a pion conversion, absorption into a proton, and then production of an axion. Despite the small number of pions in a supernova, because they are heavy compared to the supernova temperature, which is 30 MeV, this process is very important, and is even more important than the one before. So putting everything together, we can we can run simulation from with supernovae, including axions produced by these two mechanisms, which you see here. The orange line is the axion produced by bremsstrahlung, and the blue line is axion produced by pion conversion. We have these axions produced with these spectra, which are very different. The second spectrum is very non-thermal, peaked with energies higher than the pion mass. And the energy subtracted in this way to the supernova accelerates the supernova evolution, which is constrained by observation of the supernova 97A. And so we put this bound that you see here as the constraint on the axion mass must be smaller than 10 milli-electron volts to satisfy these observations. But not only, because axions produced by the pion conversion with the very hot non-thermal spectrum, they could be also detected in our detector, in our Cherenkov detectors by this process. The axion is absorbed into a nucleon, and then a pion is produced. This process is very important and could be estimated 1,000 events for a closed supernova at 1 kiloparsec. So this is still a work in progress, but we are working to directly detect axions from the next galactic supernova. Now, we can also consider, now we have discussed QCD axion in supernovae, but then let's pass to the most general case of axion-like particles and their important coupling with photons. So again, similarly to the HB case, ALPS are produced in supernovae by the Primakov conversion and the inverse decay, which now play an important role also to give some hints on the supernova physics, as we will see. And requiring that the axion luminosity is smaller than neutrino 1, we calculated that this violet region is excluded by the parameter space. And so this is the discussion before, the plot that I showed you before for the HB bound. Here is the bounds from astrophysics, which are quite important. But as you see in this region here, where the inverse decay is very important, axions are very massive, they could also decay inside the star before escaping. And if they decay inside before escaping, they could deposit energy, as also a neutrino, standard neutrino do. And depositing energy in the shock wave, they could revitalize the supernova explosion, because we know that supernovae are very hard to model with their explosion, and there is space for new physics to work at this level. So axions with parameters within this red line could also help, or in any case modify, the supernova explosion. But for studying this, we need more refined supernova simulations, including axion decaying. Axions not only are produced from the supernovae, so we observe these indirect searches, but we can also hope to detect some direct signature. For example, axions are produced in supernovae, as we discussed before, by this process, the Primakov one, and then they escape. But when they escape, they could either decay into photons or convert into external magnetic fields into photons, giving rise to a gamma ray flux, which is measured and observable, the standard one, I mean. And if we see an excessive gamma ray flux, it could be due to the axion production, due to axions. So in this case, we can also give a look to axions produced by the all past core collapse supernovae in the history of the universe. Every supernova so emits an amount of axion, which still lingers today, and composing the so-called diffuse supernova alpha background, which is very similar to the same neutrino diffuse background, which is this black line here, flux as function of the energy, and this is at lower energies compared to the axion flux, because axions typically are weakly interacting compared to neutrinos, and so they decouple before in the inner part of the supernova, and so they are hotter compared to neutrinos. So this diffuse flux is completely homogeneous in the universe, but then axions encounter the magnetic field of our galaxy. And the magnetic field is strongly non-homogeneous, as you can imagine. For example, and then axions, when pass through a magnetic field, they could convert into photons. And this is a plot, a schema of the conversion probability of axion into photons, looking the center of our galaxy. And from this complex morphology of this signal, we can put constraints on the axion properties, because the observed flux is very different from this one, and so we can constrain axions in this way. So this is an example of the gamma ray map observed with the Fermilat, which is, here you see a very high abundance of gamma rays from the galactic center. But this picture is very different from the predicted alpha flux, because the predicted alpha flux is this one, which is completely different in morphology. So it could be very useful to constrain, to do a precise analysis, comparison between with the Fermilat data, to give a constraint on axion properties. So this is the bound that we obtained, this red region here. This bound is an improvement of a previous bound calculated only by requiring that the total flux is smaller than the observed one, which is this dashed line here. But then, our bound now is this region, dashed region here. This one is pink region, and which includes also an uncertainty band related with the probability of supernova explosion or supernova failure, because very high masses in supernovae, they could fail in their explosion, producing a smaller axion flux. And not only in this uncertainty band, which is important in this kind of searches, because we have to compare with other bounds, so we need an uncertainty band. In this uncertainty band, we are also considering the different morphologies of the potential different galactic field models. And this is the resulting bound with the uncertainty compared with bound from CAST, which is this orange region here, which is one of the strongest bound at the moment, because it comes from axions produced in the sun, and tried to convert this experiment. CAST tried to convert axions into the magnetic field of its detector to observe photons, and so this is a very solid bound. I mean, but our bound in the low mass region is even stronger than this one. And the axions are important in this low mass region because they could also explain some anomalies due to this kind of oscillation, some anomalies in axion, in gamma ray fluxes, observed in gamma ray fluxes. And not only, this search is comparable with the axion bound coming from axions produced in a supernova, 1987A, and decaying and converting into photons. So this is more stable than this other bound because this is based only on the observation of a single supernova, while this other one is comes from a constant measurement that we can always improve of the gamma ray flux. And so, so in conclusion, oh yes, also less. In conclusions, axions and ALPS play a major role in astrophysics because they are a window on a very high energy scale that we can not only probe in this indirect way with by looking at very weakly interacting particles instead of going to very high mass particles. So this is a complementary research to compare to collider physics. Not only, there are also more open questions on axions in astrophysics. For example, for low mass stars, axions can transfer energy by decaying if they are massive enough. And this process could alter the energy transfer inside the star and so the stellar evolution. We are working also on that. There are also other questions, even more interesting questions in the case of supernova axions, because axions can be produced with a strong magnetic field of hypernovae, giving rise to observable signatures. Not only axions, we have not considered axions coupled to electrons here, not only to nucleons, but in general, axion-like particles can be coupled to electrons, and it's extremely interesting to see their interaction inside a supernova environment, which is very dense and so very extreme. But not only, we have also worked on axions and their relation to the observed 511 Kivi line. So maybe axions decaying to electrons could contribute to this line, and we studied this. And there are also a lot of other questions for the axion conversion, which is very important for turbulent magnetic fields in galaxy clusters, for example. So axions are very important frontiers for astrophysics, and they are catalyzing a lot of attention from the physics society now. So thanks for your attention.
Thank you very much for your nice talk. We have a couple of minutes for questions and comments. Please go ahead. Yes? Okay, if no any questions, we move to next speaker.
Okay.
Hi, Professor Hajkarim. Please sharing your screen and put your pictures on.
Sorry, you should, I think, allow me to share. Okay.
Yeah, please screen. I see your picture, but no screen.
Can you see my slides?
Yes, no, it's right. No, it's okay.
Okay.
Please go on.
Hello, everybody. I will talk about the production of thermal K-series axions in the early universe. My talk will be based on these two papers that are done in collaboration with Francesco Dramo and Soroush from University of Padua and Padua INFM. This is a schematic view of the history of the universe. First, we have the Big Bang, and then we have the inflation, and the particles are produced after heating by inflation in the particle era. For example, dark matter particle or any beyond the standard model particles. are produced in this era, and also light species that can contribute to the number of effective neutrinos can also be produced in this era and pass through different cosmic eras to reach us until today. My talk will be mainly based on the axions that are produced thermally in the early universe, and they behave as a dark radiation. The dark radiation is called the discrepancy between the theoretical number of effective neutrinos and the observed value from the CMB and Big Bang nucleosynthesis. This value is around, the theoretical value is around 3.044. And any extra degrees of freedom from the dark sector or beyond the standard model physics that contribute to this theoretical value will have some impact on the CMB and isotropy power spectrum. The strong neutrinos, axions, and possibly gravitational wave background may have some contribution to that. And future CMB experiment can put a stronger bounds on the value of the light relics or the value of delta N effective. Depending on the nature of this dark radiation particles or light species, they can have decoupled from the thermal mass of the early universe at different temperatures. And as I said, they can be connected to the new physics. Here we try to estimate the accurate amount of dark radiation from general dark radiation, and especially the axions, which in practice it depends on the considering the precise thermal background of the standard model in the early universe before the Big Bang nucleosynthesis, and also the possible production channel of the dark radiation, for example, axion, that we should consider how the axion interacts with this model background. For the thermal background of the standard model particles, we need to consider the entropy and energy density of the thermal background of a standard model, which depends on the degrees of freedom of the entropy and energy density of the standard model. This can be calculated by considering the effect of neutrino decoupling, hadron resonance gas, and also the effect of lattice QC, the equation of state around the QC transition, which is around 150 MeV, and also the effect of the electroweak crossover transition around 100 GeV. When the electroweak symmetry is broken. In the standard model, the QCD transition and electroweak transition at vanishing baryonic symmetry or crossover, and we expect that the equation of state of a standard model be smooth and crossover at different temperatures. These two plots in the left and right shows the entropy density degrees of freedom and energy density degrees of freedom calculated by these two papers, considering different lattice QCD simulation and different treatment of the electroweak transition at 100 GeV, and also considering the hadron resonance gas and neutrino decoupling at the 1 MeV and 1 MeV for neutrino decoupling and 100 MeV for the hadron resonance gas model. If we consider different type of dark radiation depending on when they are decoupled and using the standard model equation of state in the background, we can have this plot based on this formula for the value of delta N effective versus different decoupling temperature of the dark radiation or light species particle that are relativistic today and will have some impact on the tail of the CMB and isotropy power spectrum. As you see, for a scalar wild fermion, a massive vector boson, or a dark fermion with a small amount of mass that can decouple relativistically at different temperature, we can have some constraint by Planck and by future CMB stage for experiment. The future CMB stage for experiment can put stronger constraint for different light species or dark radiation particles that are decoupled at temperatures higher than the QCD transition temperature, which is around 150 MeV. So these regions above the 150 MeV for the decoupling temperature can be measured by the future CMB-SH4 experiment. An axion as a scalar will be proportional to this green curve. QCD axion is a solution for the strong CP problem, and it can also explain the tiny value of the neutron electric dipole moment, and it can be connected to the UV completion physics through Pechai-Cohen symmetry breaking. That this symmetry breaking can give mass to axion as pseudo-Nabok Goldson bosons. The QCD axion can play the role of dark matter or dark radiation if it is light, and it depending on its production mechanism. The QCD axion will have the mass of around microelectron volt when the QCD decay constant is around 10 to 12. The axion decay constant is around 10 to 12 GeV. There are different bounds on the value of Fa, the axion decay constant, from laboratory astrophysics and cosmological experiments. The supernova constraint can put a lower bound on the axion decay constant, and the upper bound on the axion decay constant Fa comes from the overclosure of the universe. But in general, the constraints on axion decay constant can be model dependent. To compute the value of the axion yield as produced thermally in the early universe, we need to solve the Boltzmann equation for the axion production from the scattering of the standard model particles. When two standard model particles meet each other and scatter, there will be another standard model particle in the final state and axion in the final state also. Because the axion is almost massless, or it has a very light mass, it will be produced relativistically in this interaction, and it will be still relativistic at 2 days. So it will contribute to the number of delta effective, which is the number of which is proportional to the number of also neutrinos as a light species. To solve the Boltzmann equation for the axion, we need to compute this gamma as a axion, the scattering rate, and also we need to have a precise value of the evolution of the Hubble rate at different temperatures in the early universe. To compute the scattering rate, we need to first compute the cross-section of the axion production from this equation. QCD axion can have different interaction with the standard model particles depending on the model that we consider for them. The general Lagrangian for QCD axion will be like this, and axion can have interaction with different gauge bosons and different fermions of the standard model, depending on the model. We can put different couplings or removing some of the coupling of the axion with the standard model particles. Above the QCD transition, around 150 MeV, we should consider the perturbative regime for the QCD, and we should consider the gluon and quark interactions with axion. And below the QCD transitions, because the quark and gluons are confined, we should consider the interaction of axions with hadrons, and especially pions, because pions will play the major role in the axion interaction below that temperature. We have considered two specific and famous axion models in our work. First, the K3Z axion, that above the QCD transition, axion couples to the gluons, and below the QCD transition, it couples to hadrons and mainly pions. We also considered the coupling of axion to kaons, neutrons, and protons, but the main contribution of the two axion production comes from the axion coupling to the pion. Above the temperature lambda n, which is around 2 GeV for our work, we consider the perturbative QCD regime, and below the 100 MeV, we consider the pion scattering for the effect of scattering of hadrons that can produce thermal axions. For temperatures above lambda n, which is 2 GeV, we also consider thermal effects on quark and gluon scatterings. These thermal effects are encoded in this gamma GG function, which is a function of temperature, and it mainly shows the production rate of axion from glue scattering to axion. And it is encoded in the F3 as a function of temperature. This function was previously calculated by other people at temperatures above 10 to 4 GeV. But for a smaller value of A, one need to calculate the value of the F3 functions at temperatures below 10 to 4 GeV that we computed in this plot. And we also considered the effect of the quark masses on the evolution of this F3 function, which was not considered before. This plot is also useful for the DFS axion model that axion, in addition to have coupling with the gluon, they also couple to fermions and other standard model gauge bosons. In the case-Fizi model, at high temperatures, we computed the axion production rate from the gluon scattering above temperature 2 GeV and below the temperature 150 MeV, or the temperature that the chiral perturbation theory is important for the hadron scattering. We consider the scattering of the axion, we consider the production of axion from pion-pion scattering. We have another scale in this plot, which is 62 MeV. The 62 MeV regime is when the next to leading order calculation of the pion and axion can be important. And we try to consider these two temperatures just to show how much our estimation for the region that we have the strongly coupled fluid is valid. In the region between these two black rates from pion-pion and glue-glue, we interpolated our result because the QCD transition at vanishing baryon asymmetry is crossed over. This interpolation can be valid. We do not expect any discontinuity in the thermodynamic variable. So we believe that what we did is correct. And based on that, we try to calculate the axion yield for the case-Fizi axion. We also consider the model at higher temperatures near the Pechaiko breaking scale, and considering also the Pechaiko fermion, which is shown by M psi, and we also calculated the production rate of axion for that. And we included that in the Boltzmann equation to find the value of the delta effective from QCD's axion scattering. The value of the delta effective that we calculate will be proportional to the axion yield to power of 4-7. And this factor comes from this numerical factor and the degrees of freedom of the axion and the photon at the decoupling. This value, as I said, can be constrained by the future CMB experiment. We can have two regimes for the axion production. When the axion production rate is larger than the Hubble rate, the delta NF will get its maximum value. And when it is smaller than the Hubble rate, the final abundance of delta axion and the value of delta effective will depend on the initial axion density. The axion yield, as shown in this plot, for 3 different values of Fa is computed. And here we assume that the Pechaiko fermion M psi to be 10 to 5 GeV. For value of Fa equal to 1.4 times 10 to 7 GeV, we reach the Planck limit. But if we increase the value of Fa, it can be measured by future simple experiment. The value that we predict for the K3 axion to be constrained or observed by the future simple experiment is 6.4 times 10 to 8 GeV. We have done the similar calculation for the DFSZ model as well. This plot shows the detectability perspective of the different axion models. Each point in this plot will be proportional to different value of FA, as shown in the x-axis. FA larger than 1.4 times 10 to 8 GeV is also valid from the supernova constraint, but the smaller than value due to the coupling of the axion and nucleons is constrained by the supernova 1987. The bound that you see in this plot are from considering different set of degrees of freedom as I showed earlier. And the magenta, blue, and green and red colors shows different value of initial temperature that we use to solve the Boltzmann equation at vanishing initial axion density. And the brown color shows the regime that we consider axion was in equilibrium with the thermal mass of standard model particles in the beginning of our calculation, or in the beginning of in the early universe. We have done, as I said, the similar calculation for the DFSZ model. As you see, the values of delta and F above 0.03 will be possibly observed by the future CMB stage for experiment. And now I discuss the DFSZ model. In the DFSZ model, more than considering the coupling of the gluon, we should consider the coupling of axion with the lepton quarks and big gauge bosons. And also we consider the 2 Higgs doublet in this DFSZ model because it can be connected to some UV completion model. As before, above the 2 GeV, we consider the perturbative QCD regime, and below the 150 MeV or 62 MeV, we consider the hadron scattering that lead to the axion thermal production. And as I explained earlier, the mainly pions will contribute to the production of the axion at low temperatures. The axion production rate below the electroweak phase transition is shown in this plot. At temperatures below 100 MeV, you see the axion production from pions and also light leptons. The axion production from tau is subdominant because the main production regime of the axion at temperature around 100 MeV comes from the pion scattering. And above the 2 GeV, the axion production will be contributed from quark and gluon scattering, and also from the axion scattering from the big gauge boson and Higgs. In this plot, we consider the value of the tangent beta equal to 10. And tangent beta is the ratio of the upper Higgs doublet and the down Higgs doublet. The V2, we have in the DFSZ model, we have 2 Higgs doublet and we have 2 waves, and V1 over V2 or VU over VD will be equal to 10 in this plot. And as before, we interpolated the regime that QCD is strongly interacting between 150 and 150 MeV and 2 GeV. And we also added the one particle irreducible correction for the standard model quarks. As you see, there is some small bound for the region that we have the bottom quark. For temperatures above the electroweak transition, above the 100 GeV, we considered the decoupling limit for the 2 Higgs doublet model, and we have only the standard model Higgs, which is around 125 GeV, and other Higgses are too heavy and their effect will be important at the temperature that is proportional to their masses. The axion coupling to the 2x doublet is shown by this Lagrangian, and because the heavy mass of the 2x doublet at temperatures below this heavy Higgses, we can integrate out the heavy mediators. This will lead to this plot for the axion production rate at very high temperatures. We consider the pseudoscalar Higgs to be around the square root 2 times 10 to 5 GeV in this plot. And we considered all the interaction of the massless quarks above the electroweak transition with the heavy Higgses, and also we considered the interaction of leptons. And we found this plot for the axion production rate above the electroweak transition. The total axion production rate for the DFSZ model is shown in this plot from temperature 1 MeV to temperature 10 to 7 GeV. And we consider the two different value of the tangent beta or the ratio of Higgs doublets in this plot. And using this plot, we calculated the axion yield for different values of Fa in the DFSZ model. And as you see, the value of Fa in the DFSZ model, the value of Fa in the DFSZ model that is in the reach of the Planck is 2.4 times 10 to 7 GeV. And the value of Fa that can be probed by future CMB stage 4 experiment will be around 5.4 times 10 to 8 GeV, as shown in this blue curve. And this is a detectability perspective plot for the DFSZ axion for different values of Fa. This vertical line are the constraint for supernova 1987 and the constraint from the white dwarf, and they are from the coupling of the axion with nucleon and electrons. And as you see, when the Fa becomes larger than 5 times 10 to 8 GeV, it can be within the reach of the future CMB experiment. And the future CMB experiment either will observe such effect in the value of delta and effective from the CMB and isotropic power spectrum, or will exclude such models. And this is a summary and conclusion of my talk. We computed the axion production rate below and above the QCD crossover transition for the KSVZ and DFSZ model. And we interpolated the regime between these two scales, because in the standard model at vanishing baryon symmetry in the universe, we do not expect any discontinuity in the thermodynamic variable and also the production rate of particles in the strongly interacting fluid. Also, we calculated the axion production rate across the electroweak transition and above that for both the DFSZ and KSVZ model. So we predicted precise interaction rate plots for these models that facilitate the future observation or prediction of the value of the delta and effective. And also we consider the uncertainty on the thermal background of a standard model, how it will affect our prediction for the value of delta and effective from different axion models. Our result can be extended to other axion models. And what we predicted can be the theoretical motivation for the future probes of the CMB stage 4 or other possible CMB experiment that plan to measure the value of delta and effective more precisely. Thank you for your attention.
Thank you very much for the nice talk. So we have a time for questions. Please ask the questions and make command if you have. Please. I asked a question to stimulate. So can you show the last PowerPoint, last transparency, the data and effective in terms of FA? Yes.
Yes.
So I try to understand better what you say. So you means this. You mean in future experiment CMS-S4?
Yes. These horizontal lines are the future constraint by CMB stage 4, and this green region is the constraint by Planck. So what we have done is we predicted the value of the delta and effective for different Axion models, basically two famous models with different initial conditions. And this value of delta and effective can change for different values of Axion decay constant FA. So depending on the
color line is a different initial condition, right?
Yes. Yes.
So when the line go below the dashed line, what does this mean?
It means that below that region, if the Axion was not initially in the equilibrium, this thermal bath, it cannot be observed. But if it was in equilibrium, it can be observed or constrained by the CMBS4. And also for the case-Fizzy model. For the case-Fizzy model, as you see in the plot, if the Axion was in equilibrium, it can be observed completely by the CMBS4. But if it's not, depending on the initial condition that you consider, either it can be excluded or observed.
I see. So the large value FA, which means coupling is smaller, and then at the end, you cannot reach. However, on the other hand, you increase temperature, initial condition.
Yes, yes.
Like a red line. Okay, I understood the figure. Okay. Any other questions?
Please.
So,
excuse me, may I have a question?
Yes, please. Any questions?
This is Muslim Zari from Isfahan University.
Please. Yes, nice.
Does this Axion particles only affect the CMB anisotropy spectrum, or they will modify the CMB polarization?
Depending on the scenario that you can consider, you can also consider their effect on the CMB polarization. So that can be studied independently, but what we did is just the CMB anisotropic spectrum, because that is what directly affect the delta and effective. So what we predicted is only for delta and effective. If you want to consider the effect on the polarization, that can be done, but I'm not expert on that.
Okay, thanks.
And it might have some effect, of course, depending what scenario you consider. What we consider here is only for case-Fizzy and DFSZ model. Maybe if you consider some Axion-like particle, it will be some effect.
Sure, thanks.
Okay, very good. We now move to the last speaker of this meeting, Soroush. Now is your turn to conclude the meeting.
Thank you.
So, can you hear me now?
Yes, yes,
So great. Can you see my screen?
yes. But no picture. Oh, picture too.
So you have to see now all the screen, yes?
Yes.
So thanks to all, everyone, participant, speakers, the people that help us in this meeting, and actually with the participation of all of you, you make this event very amazing and enjoyable. So I would like to say that we are sorry that we couldn't host you here in Isfahan for this meeting, but this situation give us some opportunity to have so many speakers from you know, all around the world. So here I would like to give some remarks about different aspects. First, I'm going to say some points about ICRANet-ISFAHAN, and then I will mention about our research activity here, a very brief summary about that. And then I will conclude on the ICRANet-ISFAHAN astronomy meeting. So, the establishment of ICRANet-ISFAHAN dates back to 2016 when Professor Rufini had a trip to Isfahan and he established officially the ICRANet-ISFAHAN Center here. And it is very pleasure for us to have this collaboration. And actually, our collaboration dates back to more than a decade. Here, you can see some photo of the this trip and the signing the agreement between Isfahan University of Technology and the ICRANet. And here you can see our starting activity, which comes back to 2010. And during more than a decade, we have several PhD students that went to the ICRANet Center, and this was the initial of our activity or research activity. And actually during this period we had so much achievement in the relativistic astrophysics in collaboration with ICRANet. And here you can see the ICRANet has several agreements with Iranian institutions. Here you can see different university and different research institution who signed the agreement with ICRANet. And actually, Isfahan has some additional value because Isfahan province hosts the international Iranian National Telescope that we had several. We had a great talk at the first day of meeting, presented by Habib Khosrowshahi, who is the head of this observatory. And actually, this meeting showed us that ICRANet and ICRANet-ISFAHAN has this potential to have to make some collaboration with this observatory, and this observatory is going to have the first light in hopefully in less than a year. And this is a great opportunity, and I think this is the direction that we have to move on that. And Isfahan can play the main role in Iran to join this different institution and to make this collaboration with ICRANet members who, you know, the ICRANet has so many agreements all around the world. More than 60 institutions has signed agreement with ICRANet, and actually is one of the biggest astrophysical, or let's say the biggest astrophysical network all around the world. So this meeting shows us the ICRANet has a great potential to have more activity in Iranian institutions and centers. So in this regard, Isfahan University Technology was a pioneer in these activities, and actually up to now we had several joint activity with ICRANet. Here you can see some webinars, and here you can see our collaboration with ICRANet in the Marcel Grassmann meeting, which is the greatest meeting in the gravitation and cosmology, which has a long history, more than several decades. So, and also we had collaboration with ICRANet in Italian-Korean meeting. We presented some contribution there. And here you can see our contribution in the Marcel Grassmann meeting, which is quite incredible. We had 4 oral talk in this great meeting. And sorry, it seems okay. Okay, here you can see also we had a parallel session. We organized a parallel session with Professor She-Sheng on the dark matter in the Marcel Grassmann meeting. And actually in that parallel session, we gathered so much the powerful speakers on this topic from different universities, and we discussed over these topics. Here, I'm going to talk about the research activities here. We were considering so far this strong field QED phenomena in the astrophysical medium and in the natural laboratories. So, since astrophysical medium like pulsars and gamma ray bursts provide some extreme region to test high energy physics, such as the well-known theory, which is quantum electrodynamics. So actually this astrophysical medium can behave as a natural laboratory to test this physics. And we have been working for the years on this, and at the same time we could provide such a extreme medium on the Earth. For example, we could have some high power lasers, some high power accelerators to test these theories. So here just I'm going to give a short review. I'm not going to talk about the detail of these topics. Here you can see also one of our work to test this QED effect by using the QED interaction in the pulsar's magnetosphere. And also the gamma ray bursts, which you have heard about them so much in this meeting, can also behave as a natural laboratory to test the fundamental physics. And actually this was one of the topics that ICRANet has been working on this for decades. So one of these phenomena was proposed by Ruffini and Damour in 1975, when they proposed some way of extracting energy from rotating black holes. And they showed that through this quantum electrodynamic process, we could explain this very high energetic phenomena. And we have been working with ICRANet on this topic, and we have published several works on high-level journals on this regard. And this was a great opportunity for me to be there for some years and also have this activity in the past years. And here also you can see one of our work, which was in the presented in the 15 Marcel Grassmann meeting on the polarization of the gamma ray burst. And here then you can see some publication in ICRANet-ISFAHAN and also our collaboration with ICRANet. this is also one of our last papers, which was about this dark matter. And actually, this was about an anomaly in experiment, which was very close to the ICRANet Center in Pescara, in Xenon 1T experiment. They were observing some anomaly in their experiment, and with our colleagues in ICRANet, we tried to explain that signal, and actually the result published in a Journal of High Energy Physics, and this is the newsletter of the ICRANet, which reported our outstanding work. This is the experiment, and here you can see the anomaly they observed more than a year ago, I guess. And here you can see this experiment is so close to the ICRANet. It's just by driving around one hour, around, let's say, around 2 hours. So here also, I would like to draw your attention to one of your last work, which was following the work proposed by Ruffini and Bonazzola on these boson stars, interacting boson stars. We considered this as a dark matter model in the neutron star, and we examined the effect of this bosonic dark matter in the gravitational wave. And our paper is going to be published in Physical Review D. So, just I can say we consider the presence of the dark matter in the neutron star, and we consider that effect on the gravitational wave spectrum as a hint of the dark matter. So let's come to the meeting, ICRANet-ISFAHAN astronomy meeting, which was be from 3 to 5 November 2021 in these 3 days. So here you can see our aim was discussing about different topics, from the ancient Persian astronomy to recent developments in theoretical and experimental physics, astrophysics, and general relativity. Here you can see so many invited speakers. Actually, we had 33 invited speakers from all around the world. And also, I have to thank everyone, invited speakers, organizing committee, and scientific committee, who did a great job and helped to make this event so fruitful and so amazing. So let's also look at the speaker list. We have Shahram Abbasi from Ferdowsi University, Mashhad, Iran, Yerlan Amirtov from Kazakhstan, Lorenzo Amati from Italy, Carlos Arguellos from Argentina, Laura Becerra from Chile, Kuantay from Kazakhstan, Pierluca Carenza from Sweden, Massimo Della Valle from Italy, Hossein Haqqi from Zanjan, and Fazlollah Hajkarim from Italy. You can see is a very long list, and it's a great pleasure for us to collect such distinguished speaker here in Isfahan as a virtual meeting. And during this meeting, we have heard about very different topics. Here you can see the program of the meeting. We started our first day of meeting with the message of the Ministry of Science of Iran, Professor Zulfi Gol, which kindly supported ICRANet-ISFAHAN activity and this meeting. And then we had a message which was presented by the Isfahan University of Technology President Sayed Mohammad Abtahi to support this activity. Our first session was chaired by Sohrab Rahwar from Sharif University, and we have started with Professor Soguti talk, who explained that how the modern astronomy was introduced into Iranian university. And then we had Professor Rufini. He explained his outstanding achievements during more than, let's say, 60, 50 years achievements on from the introducing black hole by John Wheeler up to his recent achievements on the gamma ray burst. And then we had an amazing talk given by Habib Khosrowshahi about his long-lasting effort to establish Iranian National Observatory. And actually he put this in our view that how great potential has this observatory. And after that, we had the Huntsman telescope and a talk given by Lee Spittler, which was about a Canon lens array for observing different astrophysical sources. Then we had a session which was discussing about the supernova and gamma ray burst connection. This session was chaired by Carlo Luca Luciano Bianco, and the first talk of this session was given by Massimo Della Valle from Italy, who explained us very beautiful this supernova phenomena. And then we had a great talk given by Luca Izzo from the Denmark. And then he explained us, sorry that I forgot to put the title. He explained us about the gamma ray burst from the in the optical domain. And then we had a next session which was chaired by Habib Khosrowshahi, and the first talk was given by Rio Liu from China, who was discussing about cosmic accelerator and also origin of this high energy galactic cosmic rays. And then we had Narek Sahakian from Armenia, who was explain this multi-wavelength and multi-messenger view of blazars. And then we continued the meeting with Lorenzo Amati, who discussed about cosmology with gamma ray burst, which was very interesting talks about his effort to use the gamma ray burst as a prop for cosmology. Then we had the last session of the first day, chaired by Grigory Vershchagin from ICRANet, and the first talk was given by Shahram Abbasi about black hole hyperaccretion disk and gamma ray burst, and he explained about the central engine of GRBs. Then we have an amazing talk given by Laura Becerra from Chile. He was explaining about the induced, explained about the induced gravitational collapse and the work that she did during the past years in Los Alamos on a simulation of this great scenario. And then we end the first day with the amazing talk given by Shadi Tahvildarzadeh from Rutgers University. He discussed about the role of general relativity in the structure of elementary particle. We started the second day with the amazing talk given by Professor Roy Patrick Kerr. And he discussed about the Kerr metric, and also he discussed about the different scenarios on the singularities, and he debated on some conjectures there. And this session was chaired by Hassan Firuzjai, The second talk of this session was given by Xintang Yao from Harvard, who discussed about angular momentum to a distant observer. And we continued that section with the talk given by George Roeda, who discussed about his recent work with Professor Kerr and Remo Ruffini, entitled Gravitomagnetic Interaction of a Kerr black hole with a magnetic as a source of high energy radiation of gamma ray burst. Then we continued with the next session chaired by Professor Remo Ruffini, and the first amazing talk given by Klaus Lammersal from Germany. And he discussed about some precision tests of general relativity. Then we continued with Professor Robert Prohn, and that amazing experiment, Bepi Colombo. And he discussed about this amazing experiment. Then we continued with Hossein Safari from Zanjan, who discussed about coronal plasma and some solar physics. And we finished this session with the talk given by Fatemeh Tabatabai about the recent research with the SKA. In the afternoon session of 4 November, we had two talks given by Yerlan and Liang Li from ICRANet, and they discussed about the recent achievements in gamma ray bursts and the activity that they are doing in the ICRANet, about universality of peaking time of supernova in association with gamma ray bursts. And also Liang Li discussed about self-similarity and power laws in some gamma ray bursts. And they showed us some recent result on that topics. And then we had data science workshop, and also the talk given by Mohammad Hossein Julide from IPM and Khaja Nasir University. He discussed about some classification and photometric by using machine learning method. And then we had Rahim Moradi from ICRANet, who discussed first about his recent achievements on gamma ray bursts in Professor Ruffini group in ICRANet, and then he drew our attention to some machine learning method in classification of astrophysical objects. And then we end the day with Professor Wang Yu from ICRANet, to discuss more about data science in relativistic astrophysics. We started today with the amazing talk given by Professor Hossein Masoumi about the light of the moon and Ibn Haytham and Galileo, and he discussed about some similarity and difference between a Galileo approach and Ibn al-Haytham approach, and that was really amazing talk. Then we had very great talk given by Professor Richard Kerner, who discussed about astronomy in Islamic world from a European perspective. And this session was chaired by Shahram Khosravi from IPM and Kharazmi University. Then we continued the session with Jorge Roeda, who was chaired this session, and this the session is started with a talk given by Carlos Arguellos from Argentina and ICRANet, who was discussing about dark matter fermions from linear to nonlinear structure formation. And then we had Hossein Happy from Zanjan, who discussed about MOND and the dynamics of ultra diffuse dwarf galaxies. And then we continued the day with Clement Stahel from France, who was discussing about probing the first instance of the universe with large scale structure. And then we ended the morning session with Alexander Sakharov from Russia, who discussed about shadows around the black hole as a test for the gravities. And this was our last session, chaired by She-Sheng, started by a talk with Kuantay and continued by 2 talks on the Axion, which was just 1 hour ago. Here, just I would like to give you some snapshot of this amazing event. Here you can see Professor Royker, Professor Ruffini, Professor Firuzjai, and Professor Yao in a one frame. And it is actually showed us how great was this event. So here also, just I would like to draw your attention to some snapshot of this meeting. And here was also the discussion in the morning about astronomy in Islamic wars from a European perspective. So here also I would like to draw your attention to the last point that Richard mentioned about the Isfahan and the astronomy in Isfahan. That was also worth to mention here. Here at the last, at the last but not least point, I would like to sincerely thanks to Professor Remo Ruffini, who was supporting us all the way. I would like to give a special thanks to Professor Youssef Subuti also. We had several meetings with Professor Ruffini and Professor Subuti discussing about all the details of this meeting. And actually, without their helps, was impossible to make this event. So also I would like to thank Grigory Vershagin, who helped us so much to manage the program. Also Gabriele Brandolini from ICRANet, also he was helping us so much during this technical staff to establishment the meeting from ICRANet. Elizabeth Natale also from ICRANet, she was helping us so much. Amin Farhang from IPM, also he helped me too much during this organization. And also at the end, I would like to thank some of my students, Hossein Fatouddin, Hani Karimi, and Aydin Momtaz, who helped me to organize this meeting. And at the final slide, also, I would like to thank my wife. You can see her at the right, Razia Pakravan. Also, he helped me too much because, you know, during this meeting, during this months, actually, I was so much busy with this meeting and I didn't put too much time for her. So thank you all of you, and hope to see you for the next meeting at Isfahan, probably in 3 years, maybe 2024.
Even earlier, and in person. I think we have, this meeting was very important. I invite everybody to enjoy, to look at nature, not only in our planet, not only in our galaxy, but the entire universe. We have to learn much new science there, to live better, to cultivate a new technological society, but especially learning about the universe, the marginal small position that we have in the universe, but the essential position which we have. Because we learn, we understand, we give the universe the possibility to exist and showing that it exists. I would like this meeting to establish this anelito all'infinito, you say in Italian, this attention to the largest part of our civilization, of our universe, and be friend in competing for understanding better the law of nature, Einstein theory, and especially our entire life in the universe. This is my dream, and I would like to thank, of course, Soroush to have been able to put together this fantastic meeting. And everybody has acknowledged, I acknowledge, of course, even stronger myself. But at the same time, let's read, because it's not only science, it's also humanism, humanity. I invite you, the last time I visited Iran, at the last day, I received a fantastic gift, the work of Omar Khayyam. Please read Omar Khayyam over and over. And the story of Omar Khayyam and how he represented the very deep society and also doing calendar, the science in it. Let's use this as a symbol for this new civilization, which is starting now, not a new civilization, but the continuation of the past civilization coming back to life.
Yes,
Okay?
yes, that was amazing point,
Okay.
Professor Ruffini, in the morning, I asked a question from Richard. I asked him what happened to that great, civilization at some point that disappeared, and you saw what he replied. He said this was some instability, something like this, and this leads to some disappearance. I think these meetings like this shows us there is no boundary between us, and we all enjoy the understanding the nature, and this is the goal of humanity.
What we should enforce, and we should have the rights. And I was, of course, honored in this to have official sponsor of this beautiful meeting, the Minister of Science of Iran. And we started with his message. We printed his message on special paper, and we will, of course, insert this message in the forefront of our book. Already tomorrow morning at 12 o'clock, I have a meeting in ICRA in Rome with Jenny Wardle, and we will start already to work toward the proceeding.
Yes.
For please make sure to convey all our deep esteem, the appreciation of his clear indication of sponsorship this scientific meeting, and make us the wish for future developments.
Sure. Okay. Also, I would like to give the Professor Subuti's message to you, because he faced with some problem and he told me, I appreciate you on behalf of him, and say you that he is not present now due to some, personal things.
Well, needless to say that without him, without the period spent in Zhanjiang and his guidance and his profound equilibrium and attention in the development of science, this meeting would have been really impossible, no matter our enthusiasm.
Yes, sure. So
this is the message of the minister Mohammed Ali Zolfigol, that will be on forefront of the proceedings.
Great. Okay. Thanks to everyone for being with us. Maybe we can going to finish somehow. Yes?
Yerlan, hurry up in writing the paper. We are waiting. We have to send. And to send to Massimo Della Valle, who inspired that paper. I see Massimo online. Massimo, be ready to read the paper and participate. That is a beautiful paper which is going to be finished possibly today.
As soon as I will receive the manuscript, will be my pleasure to go through it, for sure.
It's our paper, our manuscript. It's also your paper. Okay.
Okay, thank you so much, everyone. See you and keep in touch.
Yes.
Thank you, Soroush.
Yes, please. Who is calling?
Thank you, Soroush. Thanks. Bye-bye.
Yeah, thank you so much. Thank you. Okay, She-Sheng was calling me?
No, I say thank you, Soroush.
Thank you. Thank you.
Well, thank you, all of you. Actually, that was all of your efforts to make this event amazing. Just we managed the things, but you did the things.
Thank you, Soroush, for all your efforts and all other individuals.
Thank you so much.
Bye-bye. Bye.
Bye, and see you soon somewhere.
See you soon.
Bye.